So previously we were talking about how an electric motor functions. Okay, we started with we started with a single piece of wire. Okay, and then after that we moved on to a coil. Okay, and then we learned that the interaction between two magnetic forces, okay, or two magnetic fields actually. The interaction between two magnetic fields, which is from the permanent magnet and also the temporary magnet, because of the current flowing in conductor, okay, or wire, itu akan menyebabkan the Lorentz force, or the force because of the interacting magnetic fields. Okay, and the force, the direction of the force can be determined by using Fleming's left-hand rule, or we can draw out the magnetic fields and then kita kenal pasti which side is the stronger magnetic field bila dia sudah combine and which side is the weak one. Okay, and then we know that the force always moves from the strong magnetic field towards the weak magnetic field. Okay, very logical lah. And then from the coil, okay, we then moved on to the electric motor. Okay, and so this was the situation that I gave you yesterday lah. Okay, and of course the most important thing is that we need to understand how what is the function of the commutator. Okay, the function of the commutator is to reverse the direction of the current, okay, so that it always flows in one direction. Okay, so this is a very important thing, and I think this gambar aja is pretty clear lah. Okay, it tells you that sebenarnya this bahagian ini dan bahagian ini dia ikut sama ini. Okay, it follows together, and it follows together. So it will be contact, no contact, contact, no contact. Okay, contact, no contact, contact, no contact. Okay, but even though there is no contact, okay, I hope that you remember that the coil will still continue to rotate because dia sudah mula bergerak. And there's nothing stopping it from moving. Tiada daya dari luar. Okay, there's no outside force that is stopping it from, from rotating. Okay, and so this goes on until you finally turn off the current lah. Okay, or you turn off the switch lah, you turn on the battery, and then you will continue rotating, and then it will finally stop. Okay, just like our fan lah. Kan when fan, makan bila kamu off, dia bukan terus berhenti, dia akan slow down, it will decelerate, okay, and then it will finally come to a stop. Okay, so let's move on in our module. We need to talk about the factors that affect the speed of rotation in an electric motor. If you remember the situation that we saw the other day, okay, if we have a coil, sorry, not coil, if we have a copper rod, okay, or copper, okay, a copper wire over here, let's say this is positive, this is negative, and then over here I put a north pole, and then di sini a south pole. Okay, so first of all, tell me which direction is this copper rod going to move? To the right or to the left? Use Fleming's left-hand rule to determine this, please.
Left.
How do you get left?
Using the Fleming left-hand rule.
You sure are left-hand?
Yeah.
Okay. Actually, I think it's going to go to the right. It should be going to the right though. Don't you think so? Current is flowing here from positive to negative. So it's going to be flowing this way. Okay, so if you are here, okay, if you're here and the north is here, the south is here, means the current is flowing towards you. Third finger, flowing towards you. North to south is this way. So the force will be actually towards the right. Sorry, I'm mirroring lah, but the current is coming towards you. Sebab dari positive dia pergi negative, makan this way. So we find that, but anyway, thank you for trying. Okay, so we find that over here, the copper rod is going to move to the right. Okay, and yesterday in our class, we already established that there are at least two factors that affect how far the copper rod moves. Can you remember what those two factors are? What is the two factors that affect the motion of the copper rod?
Current.
Okay, first one is current, second one,
Strength of magnetic field.
oh, okay, strength of the magnetic field. Astaga. Okay, strength of the magnetic field. Sorry, my writing is like horrendous today. Okay, so today we're actually talking about the same thing, except that we're now transferring it to the speed of rotation in an electric motor. Okay, it works around the same principle, and we can always use our fan, okay, to help us with this. Okay, when we change the current, we change the speed of the rotation. When we change the strength of the magnetic field, if we use a bigger magnet, if we use a stronger magnet, okay, it's going to produce a bigger rotation or faster rotation lah, okay, in that sense. So that day we've already established this. Okay, relationship between the current, the coil, and the voltage supplied, the bigger the voltage, the bigger the current. Okay, and we find that the speed of rotation will increase when the voltage increase, when the strength of the magnetic increase, and now I'm going to add one more. Okay, the number of turns of the coil is increased. Previously, when we were doing this, kita hanya pertimbangkan one wire sahaja. Okay, but in reality, inside the fan over here, it's not just one wire. It is actually many, many, many wires yang dia kasih lingkarkan. Okay, that they make into a coil. Okay, so a third factor, okay, that affects the speed of rotation, besides the current, okay, and the strength of the magnetic field, okay, as you, sorry, I don't know who it is that said it just now, but thanks. That mentioned just now, okay, the third one is the number of turns in the coil. The more wires you have, okay, if it is just one wire, it's a pretty weak one. But if you have more wires around that, we call it an armature. Okay, later I will show you. Okay, so if you have one wire, one long wire, and then you make it into a coil, okay, then there's going to be a lot of, there's going to be a lot of temporary magnetic fields in that coil, because every piece of wire, okay, is going to have their own magnetic field, their own magnetic field, their own magnetic field, their own magnetic field. Okay, so when all these magnetic fields combine, it's going to produce a much bigger force. Okay, combination of many, 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 okay, magnetic fields. So the three factors that affect the speed of rotation of motor. The first one, we've established this a few days ago, current in the coil. Okay, secondly, the strength of the magnetic field. And third one, which is the one that I want to add today, is the coil with more turns. Okay, if you have a single coil, it's a very weak fan. Nothing much can be done. But if you take a long wire and you make it a loop, okay, a coil, okay, satu gegelong lah, okay, dengan banyak lilitan, okay, coil with more turns, okay, satu gegelong dengan banyak lilitan, definitely you will get a bigger speed of rotation. Okay, so state the factors which affect the speed of rotation. Okay, so this one already mentioned, increase the size of the current, your speed of rotation will increase. You increase the area of the coil, okay, the speed of rotation also will increase. Increase the strength of the magnetic, the number of turns, the distance also will increase. You increase the strength of the magnetic field, all this will increase. Okay, there is a fourth one now, which is, sorry, I don't know what this is, 1, 1, 2, 3 but okay, fine. Okay, another one we need to consider is the area of the coil. Okay, you increase the area of the coil, okay, a bigger coil, okay, will give you a bigger speed, okay, provided that the fan is the same. Okay, and so we find that there are many types of motors in this world. Remember, a motor, the function of the motor is to change electrical energy to kinetic energy. Okay, that's the main function. Change electric energy to kinetic energy by using electromagnetism. Okay, and so there are many motors in this world, but we need to learn about these two lah. Okay, ada dua jenis motor. One is called a brushless motor. Okay, and then the second one is a brushed motor. Brush motor is the one that has the carbon brush. Okay, and then the brushless motor is the one that don't have the carbon brush. We learn the carbon brush one first. Okay, because that's the basic one lah. Okay, but the brushless motor is it's a newer technology lah compared to the brushed motor. Simply because it reduces the friction. Okay, because whenever the brush touches the commutator kan, dia akan bergeser. Geseran always, resistance always affects the movement. Okay, so these are the similarities and the differences between both the motors. Okay, the brush motor and the brushless motor both have magnet and coil, and they both use magnetic force to produce the rotation. Okay, they combination of magnetic field, blah 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 blah. Okay, will produce the rotation. But these are the differences. In the brushed motor, okay, on this side, the magnet is the one that stays still. The coil is the one that rotates. Just like the one that we're doing lah. Okay, the brush motor. Then the friction between the carbon brush and the commutator will cause the carbon brush to wear out. This is a weakness. Okay, this is an disadvantage in the brush motor. Balik-balik kamu kena tukar itu carbon brush. Because dia balik-balik akan bergeser dengan commutator. Kan commutator dia touch, no touch, touch, no touch. Kan? So it's going to always bergeser. And so because of that, it will wear out, and after a while, it needs to be changed. Okay, and because of the constant brush, no brush, brush, no brush, dia bergeser banyak kan, there is going to be a lot of sparks. Okay, banyak spark akan terhasil masa di commutator. And it is generally louder lah. Okay, most of our motors which are very loud, okay, usually are brushed motors. Okay, even some fans which are very loud, okay, like if you hear this one kind of is very loud, kan? Usually they use a brushed motor. Okay, but the good thing about brush motor lah, okay, if I think by now you can already detect is that brush motors are cheap. Okay, are much cheaper than brushless motor, because brushless motor they work terbalik. The coil remains stationary. It is the magnet that rotates. And we find that when the magnet is rotating instead of the coil, okay, the efficiency is better. Okay, it is able to rotate even better. There's no carbon brush, so there's no friction between the carbon brush and the commutator because the magnet is the one that's rotating. Okay, so the coil just needs to stay put and the current just needs to continuously flow. No need to have touch, no touch, touch, no touch, touch, no touch. Okay, and then because of that, there's no sparking at the commutator. And generally, brushless motors are very soft. Okay, softer lah. Okay, compared to this. A lot of fans actually use brushless motor. Okay, maybe the older fans or the cheaper fans they may be a little bit noisy. You know the fan that you have. I don't remember whether it's this class or another class that ada orang kan dia bawa itu kipas yang ni itu bahkan. Okay, those are brushed motors. Very noisy. Generally lah. Okay, those are brush motors. Very noisy, you can hear. Even the motor yang kamu guna untuk berus gigi. So they are electric brushes, right? Okay, they're electric motor brushes. They're very noisy. Like that. And then if you turn it on very long time, it will get very hot. Okay, because it is a brushed motor. Okay, there's probably a carbon brush in there, and it is always apa itu bergeser. Okay, with the commutator. Okay. Same thing like the yang mencukur rambut. Okay, yang mencukur rambut itu bahkan definitely it's a motor. Slightly different operation because mencukur rambut is kiri kanan sajalah. Okay, but the idea is the same. Okay, the movement of the motor is the one that produces the sound. And usually cukur rambut is very noisy. There are some very silent ones. Okay, there's super silent pencukur rambut. But when you know that the motor is silent, it is probably using a brushless motor. Okay, brushless motor means the magnet is the one that's moving, the coil stays stationary. Okay, it is less likely to get hot. Okay, brush motor, contohnya macam yang pencukur rambut, bahkan you cannot turn it on for too long. Otherwise, nanti kau punya tangan tidak boleh pegang, terlampau panas. Why is it hot? Because of the friction between the carbon brush and the commutator. Okay. All right. So these are the benefits of the direct current motor, which is the brushless. Number one, there is no frictional force. Okay. Number two, because there is no frictional force, the efficiency will be higher. No energy is wasted. All the electrical energy will totally convert to kinetic energy. It won't be lost in heat energy. It won't be lost in sound energy. Okay. Very little maintenance is needed, and it is very long lasting. The biggest drawback the biggest drawback or the disadvantage of the brushless motor is that it is expensive. Yeah, generally it is expensive. Okay, so the next time, like for example, okay, guys, one day if you want to buy an electric razor to shave your beard, to shave your hair, or whatever, when you compare the price, you kind of know why some shavers they can sell for very cheap. 30 ringgit kau boleh beli. And there are some which is 99 ringgit. Because one of the biggest promises they make in the expensive one is that it is not noisy. Okay, it is a silent motor. Okay, silent motor means you are using a brushless direct current motor. Okay, useful, but it's expensive. Good, it's good quality. Okay, but it's expensive. And it's zero maintenance, very little maintenance, but it's expensive at that time. Okay, now these are two activities which I really wanted to do when we go back to school, but now since we have to do here, there's nothing really much we can do. I wanted you all to build a simple direct current motor using the stuff in the lab. You can try to do this at home, but I'm not sure whether you have all these materials lah. Okay, I guess wire is easily this one. Armature is not necessarily, but you need the magnets. Okay, and it has to be strong enough to be able to produce that movement. But this is how the simple motor will look like. Okay, so ini adalah kita punya gergelong. This is the coil. Okay, you see over here, this is the coil, and these are the two magnets. Okay, and they put it around here. So di sini diorang sambung kepada these two wires over here. Okay, diorang sambung kepada direct current. Usually it is a battery lah. Okay, and so all they need is just to turn on this one, and then this one will start rotating by itself. So this is how it would look like. Okay, take a look at this. Okay, sorry. Let me show you a longer video. Okay, notice that. Yeah. Okay, so notice that it is moving. Okay, show you again lah. Okay. Okay, so what you are seeing over there just now, okay, what you are seeing over here just now is that no one is actually twisting the thing. Tiada orang yang pusing itulah. It's actually moving on its own. Okay, but actually it is moving on its own because there is the magnetic force. Okay, there is the force because of the interaction between the two magnetic fields. Okay, medan magnet daripada magnet yang tetap dan medan magnet daripada the coil. Okay, and that's why I said we don't use a single coil, we use many coils. Okay, banyak lilitan, okay, in a gergelong. Okay, the coil with many turns. Sorry, not many coils. Coil with many turns. Okay, satu gergelong tetapi banyak putaran, turns. Banyak lilitan inside the coil. Okay, because the more lilitans you have, the more coils, the more turns you have, okay, the bigger the interaction between the two magnetic fields. Okay, so I guess maybe you can remind me about this when we go back to school. Remind me to, get you to do this lah. It's very fun. It's very fun to do. You get to build your own motor, and then like wow. Okay. Another thing that actually also I wanted you to do is to do this lah. Okay, which is what we call a homopolar motor. A homopolar motor is a little bit easier to do, except that it is harder to accomplish. All right. Okay, so that's actually how a homopolar motor works lah. Okay, you just use one battery and one magnet and as light as possible a wire. Um, Actually, we did this before. I went to a course lah. Okay, and we did this before. One of the most difficult things actually is the wire itself lah. The wire needs to be light enough. Okay, and at the same time, the contact between the magnet and the wire and the battery and the wire has to be really, really, really there lah. Okay, in the video it makes it look very easy. Okay, but actually when you try it, there is more to it than it's not as easy as you think it is lah. But it's always good fun to do. Okay, I don't know if you've watched like lately. I seem to see this on my For You page. You know, there's a platform down there, and then they have this moon, and then the moon is spinning. Okay, and then after that, you know, it's like the night light lah. Okay, and then there's a moon spinning like that, right? Okay, works around the same principle. Okay, it works around the same principle as the homopolar magnet as well. Okay, so actually, another thing that you may need to think about is the homopolar magnet, the homopolar motor. Okay, when you do it, it requires a strong enough magnet. Okay, which is always a slight of a problem lah. The magnet needs to be strong enough. Okay, the magnetic field needs to be strong enough. So it's not just like, you know, kalau setakat magnet yang kamu lekat di peti sejuk, it may not be strong enough. Okay, it needs to be a strong magnet lah. Okay, in order for it to work. But as I said, it's always great fun to do. If yeah, especially if you have all those shapes like the heart shape and everything. Okay, all right, let's carry on. Yeah, hopefully we can go back soon so that we can try to do this lah. Okay, let's answer a couple of questions. I know that you guys haven't answered this, but let's do this together. Okay, so whenever we do questions like this, it's time to call names. Okay, number one, based on the diagram below, what is the direction of the motion when the switch is closed? Okay, take a look at this now. When the switch is closed, this is the positive up here, this is the negative, so it's going to flow here, here, and come back here. Okay, so for the copper rod, this is the direction of the current. Okay, you are standing here lah. Okay, and you're looking at this. Okay, is it going to go towards A, or towards C, or towards B, or towards D? Okay, Fleming's left-hand rule. Who is the... Sorry, let me see who is here and who is not. Oh, there's 23 of you. Great. All right, let's have Jacinta.
D.
Okay, very good. Okay, it's going to go to the left. The same situation that I showed you just now. Okay, north to south, pointing up, but this one is coming towards you. So it's going to go towards the left. Okay, number two, diagram shows the left hand, which represents the Fleming left-hand rule. X represents what? Angeline. The third finger represents? The third finger, the middle finger. Is Angeline here? Angeline is not here. Oh, okay, sorry. Isabella.
B.
Okay, very good. I hope you said B lah, because I heard B. I'm not sure whether you said D. But okay, yeah, anyway, it's the current lah. Nothing to do with the potential difference. Remember, FBI. Force, magnetic field, and current. Okay, question number 3. A copper wire is connected to a circuit. This one. When the switch is turned on, the current flows out of the paper. Okay, the current flows out of the paper. Kalau out of the paper, we know that actually it is a dot. Remember, kalau X dia adalah masuk ke dalam, kertas or screen, okay, dot is coming out. Okay, so tell me, what is the direction of the force acting on the copper wire? Take out your left hand, everybody. Okay, take out your left hand. But Louis,
Left.
left. Are you sure it's going to go to the left? This thing, this thing can't go to the left, you know. It cannot move in the same direction as the magnetic field. Kan? So definitely left and right is out.
Oh.
The current is coming out. So make sure the current is pointing towards you. Then you align your second finger with the north and the south. So is it A or is it C?
C.
Okay, very good. It's C. It's going to go downwards. Okay, this way, coming out towards you. Okay. All right. Number 4, diagram shows a conductor wire placed in the magnetic field. Guys, these are all very popular SPM questions. Every year, sure, there is always one question that requires you to take out your hand and move it, contort it in such a way so that you have to use the Fleming's left hand rule. Okay, when the switch is on, the conductor wire initially moves where? Where's the wire? Oh, Nina, this is the wire. Astaga. Okay, current is flowing here, here, here. Okay, oh no, so ugly. Okay, current is flowing. Okay, the current is going to flow here. Okay, so kamu selalu mengandaikan bahawa kamu di sini lah, kamu memandang dari sini. Okay, Valerisa, W, X, Y or Z? Okay, the answer is X. Okay, because the current is flowing this way. Okay, dia menuju ke arah kamu. Kalau you are standing over here, you know, kamu menengok dari sini. Saya tahu, kalau kau menengok dari sini kan it's different lah, but you are here. Actually, no, you're not. You're not, no, sorry. Kalau kau berdiri di sini pun sama ini. But let's say kamu berdiri di sini kan. The current is coming towards you. Which means jari ketiga itu kan, kamu tunjuk ke arah kamu. Utara di sebelah kiri, selatan di sebelah kanan. So, kamu punya jari is going to go upwards. Okay, ke arah X. Right, the answer is X. Okay, number 5. Same thing again. Okay, left hand, everybody, come, left hand. Diagram 34 shows a conductor. The conductor is here. Which is the direction of the motion of the conductor when the current flows? The problem is it's not telling me where the current is flowing. Okay, you know what? Let's say the current flows here lah. Okay, current is flowing here. Okay, current is flowing this way. Where is this going to go? Is it going to go? Definitely X and W tak payah cakap lah. Okay, dia tidak boleh sama arah dengan current. So it's either going to go towards here or towards here. Okay, which way is it going to go? Oh, sorry. Jennifer?
Y? I mean C.
C, Y. Current flow is here. Utara selatan is here.
Macam dalam tu copper ada arrow pointing to the left.
Oh ya kah?
Yeah.
Macam, oh my goodness, it's so tiny. Oh yeah, okay, sorry. In your module ada bahkan ini. Okay, sorry. So correct lah, Jennifer's answer is correct. It's going to go towards Y. Current is pointing this way. Okay, so utara selatan is like this. So it's going to be downwards. Okay, all right, number 6. Diagram A shows a magnetic field produced by a conductor carrying current. Diagram B is permanent magnet. When the two magnetic fields interact, which diagram shows the resultant magnetic field? Okay, where is the resultant magnetic field? Daniel, can you answer this, please?
B.
Okay, very good. Okay, the answer is B. Identify the strong regions and the weak regions. But when you draw the magnetic field, this one and this one jangan lagi lukis. Okay, it becomes a resultant force. Okay, number 7. Oh, okay. I think we need to do this. Okay, diagram shows an arrangement of apparatus to study the pattern of magnetic fields which are formed. Okay, so yada yada. So over here, okay, we have the current flowing this way, this way, this way is going to go up. Here, this way, it's also going to go up. So what is the magnetic field pattern that is formed on the cardboard when both the switches are closed? Bila kita pasang switch, okay, we close the switch, current is going to flow. Which is the magnetic field that is going to be formed? Damir, what is the rule that we use to determine the direction of the magnetic field? Kalau ini, anybody?
Right hand grip rule.
Okay, the right hand grip rule. So memandangkan both the wires are pointing upwards. Okay, so both your right hand is the same. Kedua-dua, the magnetic field, okay, will show you an anti-clockwise pusingan. Okay, so definitely ini salah sebab sini adalah clockwise. Kan, ini salah. Okay, this one also is wrong, clockwise. This is also wrong, clockwise. So this is the only one that is correct because both are showing anti-clockwise, anti-clockwise. Okay, so we use the right hand grip rule for that. Okay, not so much kaitan dengan Fleming's left hand rule lah, but okay, fine. Alright, kembali kepada Fleming's left hand rule. Shows a conductor in a current carrying field. North is here, south is here. X means current is going into the paper. Okay, what is the direction of the force? Same thing again, okay, the same question. Brendan, can you answer this, please?
C, sir.
Sorry, what? C.
C.
C. Nope. It's A. Left hand, okay, left hand. There are a few possibilities why you may have gotten this wrong. Could be because you're using the right hand instead of the left hand. Okay. Current goes into the paper, north to south. Okay, pangkal is utara. Okay, hujung is south. So you should be pointing down. Pointing down, point your third finger into the screen. Okay, into the screen, and your ibu jari should point to the left. Okay, point to the left or some awkward version of the left lah. Okay. All right. Question number 9. Same thing. Which is the magnetic field pattern when the plane of the coil is horizontal? Okay. Take into account the current flow is this way. So begini, dia akan masuk begini and dia akan keluar macam ni. Okay. Okay. Take a look for a while. Tell me which is the correct one. Michelle, you want to give this a go?
A.
All right, very good. Okay, it is A. This side is going to go down and this side is going to go up. Okay, you use Fleming's left hand rule to determine that, and also the magnetic field. Magnetic field will tell you lah, sini kuat, sini pun kuat. So ini memang akan naik sini, ini akan turun di sini. All right, very good. Diagram 23 shows an electric motor. Now we're going to test the magnitude of the force increases when, which one? Okay, which is the correct answer? Rania, can I have Rania for this? Is Rania here? Yeah. Oh, Rania always got mic problem one. Can you answer this, Rania? If not, you just can type it in the chat so that I can see the answer. Okay, yeah. So maybe your mic can't work lah kan. It's okay. Type your answer saja. A, B, C, or D. Magnitude of the force. The motor will spin faster if okay, very good. Okay, the answer is D. Resistance of the coil decreases because when the resistance decreases, the current increase. Okay, ingat aliran sungai dalam air. When there are less rocks, there are less resistance. So water can flow faster. okay, the current will be bigger. Question 11, diagram this one, this one, this one. The angle of deflection, okay, the same question as just now. Okay, the angle of deflection theta is increased by Eliska. Is increased by Eliska. What's the answer for this? Macam mana kita mau membesarkan pergerakan itu? Make the angle bigger. Alright, very good, by increasing the current. Okay, so you find that guys, the objective questions kan dia tidak banyak lari ni. Kalau subtopic inilah, it's either going to ask you about this one, okay, or it's going to ask you about the factors that affect this one. So remember, there are two main factors, which is the strength of the current and the strength of the the magnetic field. But the third one is the one that involves the motor. The more coils you have, the bigger the force that is produced. Okay, the bigger the speed of the rotation. Okay. Now I'm going to skip a few questions. I want to go to this question now. Take a look at this question in your module. What page is this? Is it the same page? Oh no, it's not the same page. It's the next page, Makan. Okay. Question B in page 134, that one. Okay. So this is one of the uses of this one, the force, which is we use this one, the force, the Lorentz force, in our own ammeters. Bila kita supply the current, okay, there is actually, okay, a copper wire that is attached to a magnet, okay, that is nearby a magnet lah. So this will spin, okay. But the problem with this ammeter is that the magnet shape is not the same shape as this one. Okay, so we find that the scale of the ammeter is not uniform because the shape of the magnet is incorrect. So how would you change the shape of the magnet and the pattern of the magnetic field so that this becomes this will become a more uniform scale lah. Kau tengok dia punya scale ni. 1 di sini, 2 di sini, 3 di sini, 4 di sini. So dia tidak sekata. It is not uniform. We usually like our ammeters to be uniform. So how we do this is we change the magnet, okay, into this shape. Okay, we make it a radial shape. So this is called a radial magnet. Radial magnet. Okay, this is a flat magnet or square magnet lah. But radial shape, radial daripada perkataan radius. Okay, so it is like a circular shaped magnet lah. Okay, so because of that, the magnetic field, the lines will be a little bit different and it will fit better with this particular this one, because our soft iron is actually cylinder in shape. So because our soft iron is cylinder in shape, the magnet has to be radial so that you get a better concentration of magnetic field. Okay, dia punya medan magnet lebih tertumpu, you will produce a stronger magnetic field because tiada yang hilang bah. If you put straight like this, right? Okay, if you put straight like this, some of it will miss the cylinder because cylinder dia berbentuk bulat. Okay, but when you have a radial, it's harder to miss because dua-dua adalah berbentuk bulat. Okay, so I wanted to answer this question for you and not the two previous ones. You will know why in a while. Okay, because I wanted to teach you this. Okay, that in the ammeter, actually, there are also magnets. They are working on the same principle, okay, as the fan, and as everything. It's just that the scale is much smaller. Dia berpusing and then dia berhenti. Okay, and then when you take out the magnet, it goes back to its original position because of the control spring. All right. Okay, let's turn to the next question. Diagram 8.2. Okay, so this is a very standard question. You are given 3 types of electric motors. Okay, so electric motor X, electric motor Y, and electric motor Z. Okay, and we want to see what is the conditions there are. Okay, so electric motor X, we have 50 turns. Electric motor Y, we have 10 turns. Electric motor Z, we have 50 turns. Okay, besides that, electric motor X, we have 3 batteries. Electric motor Y, we have 1 battery. Electric motor Z, we have 3 batteries. Okay. Thirdly, electric motor X, we have semicircular shaped permanent magnet. Electric motor Y, we have a rectangular shaped motor magnet. And electric motor Z, we have a rectangular shaped permanent magnet. Did I say motor magnet? Sorry, permanent magnet. Okay, so these are the differences between the three. So let's analyze them one by one. The number of turns in the coil. Which is the suitable number of turns in the coil? Adam, how would you answer this? And why?
A lot, 50 turns,
Why?
to increase the speed of rotation.
Okay, thank you. So number one, and as I've mentioned much earlier and many times, we never give the number. Okay, the first answer was much better. Okay, Adam, a lot. Okay, or we say a bigger number of turns. Okay, never give the number in case you miss the mark. Okay, be very careful with this. Okay, so we say a bigger number of turns to increase the force, to increase the speed of the rotation, to increase the strength of the magnetic field. Either one is fine. Okay, you can give all the reasons also lah. And so we find out that the reason is always, always the same one. Increase the force, increase the strength of the magnetic field, blah, blah, blah. Okay. Secondly, the number of batteries used. Who else haven't I called? Lester.
Bigger.
Okay, bigger, why?
Increase the current.
Okay, very good. Okay, we use a greater number of batteries to increase the current, because when we increase the current, we will increase the speed of rotation, blah, 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 blah. Okay, shape of the permanent magnet. Okay, shape of the permanent magnet. Can I have Miss Tian for this, please?
Rectangle.
Why rectangle?
Bigger. Call what? Bigger magnetic field.
Bigger magnetic field. If we use a rectangular one, it will be a bigger magnetic field. Okay. Technically, your reasoning is not correct. Your reasoning is not wrong. Okay, when you use a rectangular one as opposed to a semicircular one, okay, of course the rectangle one generally the surface area is bigger lah. Okay, dia punya luas lebih besar, and because dia punya luas lebih besar, dia punya medan magnet pun akan menjadi lebih besar. Okay, but actually we need to take into account what are we actually making the rotation for. This motor is to move the fan, and when you look at how the coils are placed, right? They're actually placed in a cylinder. Okay, in a cylinder case, just like our ammeter case just now. So actually, the best shape would be the semicircular shape. Okay, but the reasoning is not wrong. Okay, the reasoning is still wrong. You increase the strength of the magnetic field, and okay, you increase the strength of the magnetic field, but we have a radial magnetic field. So a lot of things depend on what kind of shape we are making the coil. If our coil is around a cylindrical shape, then it is better to use a radial magnet. If our coil is square, okay, or rectangle, then it is better to use a flat magnet. Okay, so everything depends on how we make the coil. Okay, but it's going to be very funny lah. You look at the back of your fan, right? Okay, the back of your fan, sorry, I don't know if you can see this. Okay, back of the fan over here is cylindrical. So you kind of know that the magnet over there is a semicircular shaped magnet lah. Because if we want to use a rectangular magnet, then the butt of your fan will be very rectangular, and over here will be very sharp. And kalau dia tiba-tiba terjatuh di atas kaki kamu, it's going to be very painful lah. Okay. Although technically, I think that if you use a rectangular magnet, the magnetic field will be stronger. Not so concentrated, but there will be more. There's a bigger area lah. Okay. But I guess when people designed the fan, they decided to use a cylindrical butt, so that it's less dangerous, and nobody's legs and arms will get injured if the fan falls on their feet, okay, or on their head lah. So, so I think that's the reason why lah. Okay, so that's it. That's it for this subtopic. And your homework for today is the two missing questions which I didn't answer. I purposely didn't answer because you know why? What is the first question? Take a look. The first question. The first question is the one that I asked you to memorize. Okay? What is the direction of motion? Explain the motion of the copper wire XY. That's the one that I asked you to memorize. Okay, so write your answer over there. And then question number 2, A, everything, including this drawing over here. Okay, so the same thing as we have been doing this whole week. Answer this. Okay, then snap a photo of the entire page. One photo enough. Don't go and snap every single line and then okay, one photo enough. Okay, just make sure that it is clear enough for me to read. Okay, so that I can see lah. Okay, but please send one photo only. Don't send so many. Otherwise, it's just going to clog up the comment section. Okay, so finish it. If you actually you should be finishing it by today lah. I'm trying not to give you homework that carries on forever and ever. But the flip grid video, the deadline is tomorrow.